All right, so this is the second video for exponential modeling in AP Calculus, section 6.4 from your textbook. So as we previously discussed, the concept of exponential growth and decay leads to the general function y equals y sub 0 e to the kt, which comes from the differential equation dy dt equals k times y. So if k is greater than 0, as previously discussed, it would be considered an exponential growth function. Some examples of that would be population growth, compound interest, different things like that. Spread of disease. K is less than 0 is a decay function, and one of the most common examples of that would be radioactive decay. So we're just going to look at some different scenarios of, depending on the information you're given, how you could create an exponential model. So here, for example, on A, it says k equals 1.5 and y sub 0 is equal to 100. Now, if you remember that the function is y equals y sub 0 e to the kt, then you would immediately recognize, oh, okay, my function would be y equals 100 e to the 1.5t. So that should be my answer. But let's say that you didn't remember that, but what you did remember is that always and forever, your differential equation is dy dt equals ky. So how could that differential equation lead me to y equals 100e to the 1.5t? So to get that, I could separate my variables as I've been doing, integrate both sides, and so we would get the natural log of the absolute value of y equals 1.5t plus c. Then remember, we insert an e on both sides to get rid of the natural log, and that brings the constant in front as a multiplier coefficient. So then if we use the fact that y is 100 when time is 0, that's how we get a constant value of 100, which leads us to y equals 100 e to the 1.5t. Okay, so if they ask you to use a differential equation to find the exponential model, then you have to do it that way that I just did it with the separation of variables. But if they don't, then you don't necessarily have to do that. Now, one way that the differential equations could be helpful is when you have a situation like this, where they did not give me a k value. They gave me two different values at two different times, and I'm going to need to figure out the k value from that. So if I solve this as a differential equation, I've just got k times y. So again, going through the exact same process again of separating the variables. So you get y equals ce to the kt. Now it would be at this point that either I would have a k value or I could solve for c. Well, I can solve for c using either one of the values that have been given to me, the 0 and the 50, or the 5 and the 100. If I choose to use the 0 and the 50, that will actually give me e to the 0, which would give me then y equals 50 e to the kt. And it wouldn't be as difficult to solve for my value of c then. So then that is then what I could use to solve for k. So since I've already used the 0 and the 50, now I'm going to use the 5 and the 100 to solve for k. So for that, y would be 100 when t is 5. So now to solve that for k, I would first divide by 50, so I would get 2 equals e to the 5k. Now to undo the e, I would take the natural log of both sides. And so then k would be natural log of 2 divided by 5. Do not find what that is as a decimal. Just leave it like that. So if we put the k now back into here, we get a final answer of y equals 50 e to the natural log of 2 divided by 5 times t. And so that would actually be your exponential model for this problem. So another common thing that exponential models are used for is for carbon dating. You may have done this in chemistry. where you have the half-life of a radioactive substance. So half-life literally means the amount of time for half of the substance to be left. They use it in carbon dating if you have like a really, really old fossil and they're trying to figure out how old it is, or you find a body in the woods and they're trying to figure out how old the body is, or how long it's been in the woods. That sort of stuff is what they would use, the carbon dating. So this is just a general situation though. We just have a decay equation of y equals y sub 0 e to the kt. Well, y sub 0 is at time 0 our initial amount. What we don't know is the time to become half of y sub 0. But those are our two coordinate pairs that we're going to substitute into here. So at some time that I don't know, I would have half of my original amount there. But if I'm trying to find the half-life, that means I'm trying to solve for how much time it would take to get to half the amount. So I'm actually going to solve this equation for t. Now, if you notice, you have a y sub 0 on both sides, so those will actually cancel out. So you have 1/2 equals e to the kt. Now to get rid of the e, I would take the natural log of both sides, and then the natural log of 1/2 divided by k is the time it would take. So whatever my rate of decay is, k, which they would have to give me, I just take the natural log of 1/2 and divide it by that, and that's how much time it would take to decay to half the amount. Now, they may write it a different way though. So let's talk about properties of log again, real quick. Natural log of 1/2. This is a fraction inside of the log, so I can actually separate it into natural log of 1 minus natural log of 2. Natural log of 1, though, is 0. So this is actually negative natural log of 2. So it's possible that they would write it like that. I just don't want you to be confused if you don't see a natural log of 1/2. If it was an FRQ, natural log of 1/2 is perfectly acceptable. Okay? All right, so that would work for all half-life problems. Here's another situation. I'm just throwing lots of different things at you. So suppose the bacteria in a colony triples every hour beginning with 2. How many bacteria will the colony contain after 18 hours? Okay, so at time 0, we've got 2 bacteria. And then it says it triples every hour beginning with 2. So I actually know that after 1 hour, I would have 6 bacteria. Now I could just sit here and keep tripling the amount, multiply by 3, multiply by 3, multiply by 3, until I get all the way to 18 hours. So if I absolutely had to, I could do it that way. But I could also use my general exponential growth differential equation. And so, yet again, we are solving this differential equation. So I'm not even talking through the steps anymore because it's the same every time. First thing we need to find is we need to find C, and then we'll worry about finding K. This is kind of like the problem we did a few minutes ago, example 3b, where we have 2 coordinate pairs. So to find C, I'm going to use my initial amount at time 0. So that would be 2 equals C times 1. So that tells me that my equation is at least y equals C2 e to the kt. Now to find k, I'm going to use the other coordinate pair. So y is 6 when t is 1. So that means that 3 equals e to the k. So the natural log of 3 is my k value. So my function is now y equals 2e to the natural log of 3 times t. So that model I could use for any problem. The particular problem that they have here is how many bacteria will be in the colony after 18 hours. So for 18 hours, we would have y equals 2e to to the natural log of 3 times 18. And there really is no shortcut for that at all. So you would just put that in your calculator, and it would end up being 774,890,000, or excuse me, 840,000. 978. So 2 bacteria in less than a day have turned into almost 800 million bacteria. That's how disease spreads so quickly. One person's sick, and next thing you know, the whole school is sick. Okay? All right, so example 6 here. It says, in the course of any given year, the number Y of cases of a disease is reduced by 20%. If there are 10,000 cases today, how many years will it take to reduce the number of cases to 1,000? So at time 0, we've got 10,000 cases. In 1 year, it'll be reduced by 20%. I don't really care that it's reduced by 20%. I care that 80% of the people will still have the disease. So 80% of 10,000 means that in 1 year, 8,000 people will still be sick. So then we'll worry about the reducing the cases to 1,000 again. So I want you to pause the video, and I want you to work through the exact same process that we just did in example 5 to come up with just the general formula function. And then we'll worry about solving for the 1,000. All right, so all of my writing in blue is my process for separation of variables and then solving for C. Solving for C, I came up with Y equals 10,000 e to the kt, and then I used the 1, 8,000 to find my value of k. That's written in red. K was natural log of 0.8. So now I have a general function of Y equals 10,000 e to the natural log of 0.8 times t. So now if you look at the final question though, it says, if there are 10,000 cases today, how many years will it take to reduce the number of cases to 1,000? So we know that we want to end up with 1,000 cases using this model. So we just need to solve it for t. So we divide by 10,000, you get 0.1. And then we would insert the natural log on both sides to get rid of the e. And so your time is going to equal the natural log of 0.1 divided by the natural log of 0.8, which is 10.319 years. All right, one last problem here. Carbon dating. So this goes back to the half-life we were looking at back in example 4. So it's 5,700 years is the half-life of carbon-14. Find the age of a sample in which 10% of the radioactive nuclei present have decayed. So we already figured out that the time would be equal to negative natural log of 2 divided by k. The only problem is we don't know what k is. But what we do know, if we back it up a few steps, is that we've got y equals y sub 0 e to the kt. 5,700 years is the half-life. So actually this isn't going to help me. So that means that it takes, your t is 5,700 years in order to get half of the amount remaining. So 1/2 equals e to the 5,700 k. Natural log of 1/2 equals 5,700. Forgot my 7. 5,700 k. Divide, and so you get k equals negative natural log of 2 over 5,700. And if you don't understand why that's negative natural log of 2, go back and look at example 4. So now I want you to pause the video, and I want you to see if you can figure out what the original function would be and the age of a sample in which 10% has decayed. All right, so I worked everything out over there on the right. If 10% has decayed, then that means 90% is left, so that's where the 0.9 comes from. Substituted in my k, solve for t, and got my 866.4.